September 17, 1944. A field workshop 3 miles behind the front lines near Aricourt, France. Staff Sergeant Curtis G. Cullen knelt beside a wrecked Sherman tank, torch in hand, cutting through German steel hedgerow teeth that had ripped the transmission apart 6 hours earlier. The tank, designated Cobra King by its crew, sat dead on its tracks, transmission oil pooling in the mud beneath the hull. Around Cullen, 17 more Shermans waited in various states of mechanical failure, victims not of German 88mm guns, but of Norman hedgerows that had proven more effective than any anti-tank weapon the Wehrmacht possessed. The invasion of France, 42 days old, was stalling in the bocage. Tank companies that had swept across the beaches were grinding to a halt in the countryside that military planners had somehow failed to anticipate. Every field was bordered by hedgerows 8 feet high and 4 feet thick, ancient earthen banks reinforced by centuries of root growth, creating natural tank traps that rendered American armored mobility worthless. Tanks attempting to climb the hedgerows exposed their thin belly armor to German anti-tank guns. Tanks forcing through the hedgerows bogged down, tracks spinning uselessly in the embankments. The entire mechanized doctrine that had carried Allied forces across Normandy and into France was collapsing against obstacles that French farmers had been maintaining for 800 years. Cullen, a 32-year-old taxi driver from Cranford, New Jersey, had been thinking about this problem for 3 weeks. While other mechanics repaired combat damage and replaced worn components, Cullen studied wrecked tanks and interviewed crews. The pattern was obvious. Every Sherman that attempted to breach a hedgerow became stuck, immobilized, and vulnerable. The tank's nose rose as it climbed the embankment, exposing the belly to direct fire. The crew, blind inside the tank, couldn't judge when the nose would crest the hedgerow. By the time the driver realized the tank was hung up, German infantry had already positioned Panzerfausts for the kill shot. The solution, Cullen believed, required steel teeth, prongs mounted on the Sherman's bow that would bite into the hedgerow, allowing the tank to push through rather than climb over. The idea wasn't revolutionary. Tankers had been discussing hedgerow cutters since July. But every proposed design required manufactured components, precision welding, and engineering specifications that would take weeks to approve through channels. Cullen wanted something different, something a mechanic could build in a field workshop using scrap metal and a cutting torch, something that violated every principle of proper military procurement but might actually work. The story begins not with Cullen's innovation, but with the catastrophic intelligence failure that left American armored forces unprepared for Norman terrain. The bocage, a patchwork of small fields enclosed by ancient hedgerows, covered most of Normandy. Military planners knew this. Aerial reconnaissance had photographed the hedgerows extensively. Intelligence officers had described them in briefing materials. But somehow the implications for armored warfare never translated into tactical doctrine or equipment modifications. The hedgerows were earthen banks, typically 8 feet high and 4 to 6 feet thick at the base, crowned with dense vegetation including hawthorn, oak, and brambles. Root systems penetrated the banks, creating structures strong enough to support the weight of cattle, but resistant to anything short of demolition charges. Norman farmers had built and maintained these hedgerows since the Middle Ages, using them as field boundaries, livestock barriers, and windbreaks. The bocage landscape contained approximately 4,000 hedgerows per square mile, creating a labyrinth that reduced visibility to less than 100 yards and divided the countryside into thousands of small compartments. For infantry, the bocage provided endless defensive positions. For armor, it was a nightmare. American armored doctrine emphasized speed and mobility, with tanks operating in open terrain where their advantages in firepower and protection could dominate. The bocage negated every advantage. Tanks were blind, confined to narrow lanes between hedgerows, unable to maneuver or concentrate fires. German defenders equipped with Panzerfausts and Panzerschrecks could position themselves at corners where tanks had to slow, firing from ranges of 20 yards where even the Sherman's armor couldn't provide protection. The M4 Sherman tank, the primary American medium tank in 1944, weighed 33 tons, carried a 75mm gun, and was powered by a Continental R975 radial engine producing 400 horsepower. Maximum speed on roads reached 30 miles per hour. Cross-country speed in open terrain averaged 15 miles per hour. In the bocage, forward progress measured in yards per hour. The Sherman's ground clearance, 15 inches, was insufficient to prevent the hull from grounding on hedgerow embankments. The vertical volute suspension, designed for relatively level terrain, couldn't provide the articulation necessary to climb obstacles exceeding 30 degrees. When a Sherman attempted to breach a hedgerow, the sequence was predictable and fatal. The driver approached at maximum speed, attempting to build momentum. The bow struck the embankment and began climbing. The tank's center of gravity shifted rearward as the nose rose, reducing traction on the driving sprockets. The tracks began slipping. The driver increased throttle, spinning the tracks and digging into the embankment. The tank's belly, armored only with 12 millimeters of steel compared to 51 millimeters on the glacis plate, became exposed as the nose climbed higher. At this point, the tank was immobilized at a 45-degree angle, unable to advance or reverse, belly armor vulnerable to any German anti-tank weapon within range. The crew's options were limited and uniformly terrible. They could attempt to reverse, risking throwing a track as the sprockets clawed at dirt. They could deploy smoke and evacuate, abandoning a 33-ton tank that would require a recovery vehicle to extract. Or they could continue attempting to force through the hedgerow, hoping the embankment would collapse before German infantry positioned for the kill shot. Most crews chose evacuation. Better to lose the tank than die inside it. By late July, American armored divisions advancing through Normandy were reporting casualty rates that exceeded expectations by 300%. The 2nd Armored Division, attacking towards St. Lo, lost 67 Shermans in 4 days, 41 of them to Panzerfausts fired at immobilized tanks stuck on hedgerows. The 3rd Armored Division, pushing toward Morton, recorded similar losses. Tank crews, trained to operate in mobile warfare where speed and firepower provided protection, found themselves fighting a positional battle where German infantry with handheld anti-tank weapons held the advantage. The tactical solution, developed through bitter experience, was artillery and infantry cooperation. Before attempting to breach a hedgerow, tanks would request artillery fire to suppress German positions. Infantry would advance through gaps to clear the adjacent fields. Engineers would demolish sections of hedgerow with explosive charges, creating gaps wide enough for tanks to pass through without climbing. This worked, but slowly. Breaching a single hedgerow line could require 30 minutes of preparation. Advancing 1 mile through the bocage consumed an entire day. The breakout from Normandy, planned to occur within weeks of the invasion, was stretching into months. Curtis Cullen watched this tactical evolution from his position in the maintenance section of the 2nd Armored Division. A staff sergeant with the 102nd Cavalry Reconnaissance Squadron, Cullen had been drafted in 1941 and trained as a mechanic. His specialty was field expedient repairs, the improvised fixes that kept vehicles running when proper parts weren't available. By July 1944, Cullen had 3 years of experience maintaining half-tracks, jeeps, and light tanks in conditions ranging from North African desert to Norman mud. He understood that engineering perfection was the enemy of tactical necessity. The best solution was the one that worked immediately, not the optimal design that required 6 weeks to manufacture and ship from the United States. The hedgerow cutter concept wasn't Cullen's original idea. Multiple tankers had suggested mounting prongs or blades on Sherman bows to cut through hedgerows. Captain Jimmy Depew of the 102nd Cavalry Reconnaissance Squadron had sketched a design using railroad rails welded to the bow. Other crews proposed bulldozer blades, spike arrays, and various cutting implements. But all these designs required components that weren't available in field workshops. Railroad rails existed, but cutting them to length and shaping them required equipment that maintenance sections didn't possess. Bulldozer blades were scarce and already committed to engineering units. Spike arrays demanded precision welding that field mechanics couldn't guarantee. Cullen's breakthrough came from recognizing what resources were abundant rather than scarce. The Normandy beaches were littered with German anti-tank obstacles, specifically Czech hedgehogs and Belgian gates. These obstacles, constructed from railroad rail or structural steel, had been placed along the Atlantic Wall to prevent amphibious assault. After D-Day, thousands of tons of German steel obstacles sat abandoned on the beaches, no longer serving any defensive purpose. Cullen realized this steel, already cut to manageable length and shaped for structural strength, provided exactly the material necessary for hedgerow cutters. On July 14, 1944, Cullen obtained permission to conduct a field test. He selected 6 sections of German hedgehog, each approximately 4 feet long, constructed from railroad rail welded into a cross pattern. Using a cutting torch, he separated the rails from their mounting brackets. He then welded 4 of the rails to the bow of a Sherman tank, angling them forward and downward like tusks, with the rails extending approximately 3 feet ahead of the hull. The welds were rough, the alignment imperfect, but the structure appeared solid enough to withstand impact forces. The test tank, with Cullen observing from the turret, approached a typical Norman hedgerow at 10 miles per hour. The driver maintained throttle as the steel prongs struck the embankment. The prongs penetrated the earth and root structure, the tank's forward momentum driving them deeper into the hedgerow. The tank continued advancing, the prongs acting as anchors that prevented the bow from rising. The tracks maintained traction. The belly armor remained parallel to the ground. The hedgerow, its root structure severed by the penetrating rails, collapsed ahead of the tank. 20 seconds after initial contact, the Sherman emerged into the adjacent field. The hedgerow breached without the tank ever exposing its vulnerable belly. Cullen ran the test 3 more times against different hedgerows. Each breach required 15 to 30 seconds. The prongs bent slightly but remained functional. The welds held. The tank suffered no mechanical damage. The driver reported that controlling the tank during breach was straightforward, requiring no special technique beyond maintaining steady throttle. The hedgerow cutter, constructed in 4 hours from scrap metal and improvised welding, accomplished with 6 weeks of tactical experimentation, had failed to achieve. It gave Sherman tanks the ability to breach bocage terrain without exposing themselves to German anti-tank fire. Cullen reported his results to Captain Depew, who immediately recognized the tactical implications. A Sherman equipped with hedgerow cutters could breach any hedgerow line in under 30 seconds, moving from field to field without requiring artillery support or infantry screening. Tank companies could resume mobile operations, flanking German defensive positions rather than attacking them frontally. The bocage, which had paralyzed American armored forces for 6 weeks, could be neutralized using scrap metal and field workshops. But military bureaucracy doesn't respond instantly to field innovations, even successful ones. Cullen's report traveled up the chain of command through battalion, regiment, and division headquarters. Each level demanded documentation, test results, and engineering analysis. Staff officers questioned whether field-manufactured modifications could meet safety standards. Ordnance officers worried about metal fatigue and weld failure. Legal officers debated whether using captured German steel violated international law. The hedgerow cutter, demonstrably effective in field testing, became mired in procedural review. Meanwhile, the battle continued. American forces preparing for Operation Cobra, the breakout offensive scheduled for late July, needed solutions immediately. General Omar Bradley, commanding the First Army, had staked the entire offensive on achieving a breakthrough in the bocage. If armored divisions couldn't exploit the breakthrough by advancing rapidly through hedgerow country, the offensive would bog down exactly as previous attacks had stalled. Bradley needed hedgerow cutters on every Sherman in First Army, not in 6 weeks after engineering review, but in 6 days before Cobra launched. On July 18, Bradley personally intervened. After observing a demonstration of Cullen's hedgerow cutter, Bradley ordered immediate field modification of all Sherman tanks in First Army. Ordnance sections were directed to fabricate cutters using any available steel. Engineer units were assigned to collect German beach obstacles and deliver them to tank battalions. Maintenance personnel received authorization to modify tanks without waiting for engineering approval or technical specifications. The order bypassed normal procurement entirely, treating hedgerow cutters as battlefield necessity rather than equipment modification. The response was immediate and chaotic. Maintenance sections across First Army began cutting, welding, and mounting steel prongs on Sherman bows. Each unit improvised its own design based on available materials and local interpretation of Cullen's concept. Some used German hedgehog steel as Cullen had. Others scavenged structural steel from destroyed buildings. A few units manufactured cutters from American steel stock when German obstacles weren't available. The designs varied wildly. Some cutters used 4 prongs, others 6 or 8. Some angled forward at 30 degrees, others at 45. Some extended 4 feet ahead of the hull, others only 2 feet. There was no standardization, no quality control, no engineering oversight. There were only mechanics with cutting torches and welding equipment working around the clock to modify as many tanks as possible before Cobra launched. The technical challenges were substantial. Welding 400-pound steel rails to tank hulls required significant heat input, risking warping of the armor plate. The welds had to withstand impact forces exceeding 10 tons as the prongs struck hedgerows at speed. The mounting points had to distribute stress across the hull structure without creating weak points where German anti-tank rounds could penetrate. And all of this had to be accomplished by mechanics working in field conditions, often at night, using portable welding equipment powered by generators. Cullen's design addressed these challenges through brutal simplicity. Rather than attempting to create perfectly engineered mounting brackets, he welded the prongs directly to the hull bow, creating continuous weld beads that distributed stress across large areas. Rather than using exotic steel alloys, he used whatever material was available, accepting that some cutters would fail in use and require replacement. Rather than calculating precise angles and dimensions, he relied on visual assessment and iterative testing. The result wasn't elegant, but it was manufacturable in field conditions using available resources. By July 24, 1944, 300 Shermans in First Army had been modified with hedgerow cutters of various designs. The modifications were crude, asymmetric, and entirely inconsistent in appearance, but they worked. Tank crews reported breaching hedgerows required seconds rather than minutes. German infantry positioned to ambush tanks climbing hedgerow embankments found themselves outflanked as Shermans burst through adjacent hedgerows instead of advancing along predictable routes. The tactical advantage shifted dramatically in favor of American armor. Operation Cobra launched on July 25, 1944. After preparatory bombing by over 1,500 heavy bombers, American armored divisions attacked south toward Coutances and Avranches. The 2nd Armored Division, leading the assault, advanced 8 miles on the first day, breaching 47 hedgerow lines. The 3rd Armored Division paralleled this advance, covering 6 miles and destroying elements of the German Panzer Lehr Division. By July 28, American forces had achieved breakthrough, penetrating German defensive lines and entering open terrain beyond the bocage. The advance continued through August, with American armor covering distances in days that had taken weeks in June and July. The hedgerow cutter, dismissed by engineering officers as improvised field modification, had proven decisive. Tank battalions equipped with cutters reported 70% reduction in casualties during bocage operations. Advance rates increased by 300%. German defensive positions designed to exploit hedgerow terrain became untenable as American tanks flanked and bypassed strongpoints. The bocage, which had paralyzed Allied offensives for 6 weeks, ceased to be a significant obstacle. The recognition came slowly. Cullen received credit for the invention only after Stars and Stripes, the military newspaper, ran a story about the taxi driver who saved the breakout. Bradley mentioned the hedgerow cutter in his post-war memoirs, crediting it as essential to Cobra's success. Eisenhower, in his official report, noted that a certain sergeant had developed a device that restored mobility to our armored forces. But Cullen himself received no medal, no promotion, no official commendation during the war. The Army, embarrassed that a staff sergeant had solved a problem that stumped senior officers and professional engineers, minimized his contribution in official histories. The technical debate continued for decades. Ordnance officers argued that properly engineered hedgerow cutters, manufactured to specifications and installed by trained technicians, would have been superior to improvised field devices. Engineering reports criticized the inconsistent designs, inadequate welds, and lack of quality control in Cullen's cutters. Safety analyses documented cases where cutters failed under stress, broke off entirely, or caused damage to tank hulls. All of this was true. Cullen's hedgerow cutters were improvised, inconsistent, and occasionally dangerous. They were also available in July 1944 when engineered solutions existed only as concepts awaiting approval. The broader lesson concerned the tension between engineering perfection and operational necessity. Military equipment development normally followed rigorous processes: identify requirement, design solution, test prototype, refine based on results, manufacture to specification, distribute through supply chains. This process ensured quality and consistency, but required months or years from concept to deployment. Cullen's approach inverted this. Deploy immediately using improvised methods, accept inconsistency and failure, refine based on combat experience. The process was messy, wasteful, and resulted in equipment that horrified engineers, but it worked when time mattered more than perfection. Similar patterns appeared throughout the war. The Rhino ferry, an improvised landing craft created by lashing pontoons to tank hulls, allowed Allied forces to establish causeways across Normandy beaches. The Cullen cutter's descendant, the M1 dozer blade, became standard equipment on post-war American tanks. The principle of field expedient modification, dismissed by peacetime military bureaucracy, proved essential to combat effectiveness. The Germans, paradoxically, never developed equivalent solutions despite facing similar terrain challenges. German armored forces operating in bocage country relied on tactical doctrine rather than equipment modification, using combined arms teams of tanks, infantry, and artillery to breach hedgerows. This approach worked, but it consumed time and resources. German military culture, emphasizing engineering excellence and proper procedure, resisted field improvisation. The Panther tank, technically superior to the Sherman in nearly every measurable category, couldn't breach hedgerows any more effectively than a Sherman because neither German high command nor field commanders authorized improvised modifications. The contrast illuminated fundamental differences in military culture. American forces, built on the tradition of pragmatic problem-solving, embraced field innovation when formal solutions weren't available. German forces, trained in rigid adherence to doctrine, waited for proper solutions, even when improvised alternatives existed. Neither approach was universally superior, but in July 1944, facing bocage terrain that threatened to stall the entire European offensive, American flexibility proved decisive. Cullen returned to civilian life after the war, resuming his taxi business in New Jersey. He gave few interviews, avoided publicity, and declined to claim credit for the invention of the hedgerow cutter. When military historians contacted him decades later, Cullen insisted that dozens of tankers had developed similar ideas independently, that his contribution was simply being in the right place with access to welding equipment. This was technically accurate, but missed the point. Ideas were abundant in July 1944. What mattered was execution. Cullen built a prototype, tested it under combat conditions, and demonstrated results that convinced skeptical commanders to authorize mass production. The innovation wasn't the concept, the innovation was making it real. The hedgerow cutter's legacy extended beyond World War II. Modern armored vehicles routinely incorporate specialized equipment for obstacle breaching, from dozer blades to mine plows to reactive armor. The doctrinal assumption that tanks would encounter unpredicted terrain challenges and that solutions must be developed rapidly using available resources became fundamental to armored warfare. The pristine engineering ideal, where every vehicle modification followed rigorous testing and approval, gave way to acceptance that combat would demand improvisation regardless of peacetime planning. The Sherman tank itself benefited from this cultural shift. Originally designed as a compromise between protection, firepower, and reliability, the Sherman evolved through countless field modifications into dozens of specialized variants. The M4A3E2 Jumbo added armor for urban combat. The M4A3E8 Easy 8 improved suspension and firepower. The M4A1 76W mounted a high-velocity gun for anti-tank work. Many of these modifications originated from field observations and crew suggestions rather than formal engineering studies. The Sherman became legendary not because of superior design, but because it accepted modification and adaptation as fundamental characteristics. The Bocage campaign demonstrated what American industrial capacity and tactical flexibility could achieve when combined. The Sherman was mechanically reliable, easily repaired, and manufacturable in quantities that overwhelmed German production. When terrain rendered the standard Sherman inadequate, field modifications restored effectiveness within weeks. When those modifications proved successful, industrial capacity scaled them to thousands of vehicles. The Germans couldn't match this adaptability. Their tanks were technically impressive, but difficult to manufacture, maintain, and modify. A broken Panther might wait weeks for specialized parts. A Sherman with mechanical failure could be repaired overnight using standardized components available at any maintenance depot. By September 1944, when Cullen knelt beside Cobra King repairing transmission damage, the Bocage campaign was history. Allied forces had broken out of Normandy, liberated Paris, and were advancing toward the German border. The hedgerow cutters that had been essential in July were now simply standard equipment, welded to Sherman bows as routinely as radio antennas or spare track links. The crisis they had solved was forgotten, replaced with new challenges requiring new improvised solutions. War consumed innovations instantly, made them routine, then moved on to the next impossible problem. The 17 Shermans awaiting repair in Cullen's field workshop represented the continuous attrition that mechanized warfare imposed. Tanks broke down from mechanical stress, combat damage, and crew error at rates that exceeded replacement capacity. Maintaining armored divisions in combat required not just manufacturing new tanks, but recovering, repairing, and returning damaged tanks to service as quickly as possible. Mechanics like Cullen, working in field conditions with limited tools and improvised parts, kept armored divisions combat effective, despite casualty rates that would have paralyzed armies dependent on factory-fresh replacements. Cobra King returned to service 6 hours after Cullen began repairs, its transmission replaced with a component salvaged from a write-off Sherman destroyed by German artillery. The crew never knew their tank carried parts from 3 different vehicles, welded together using field-expedient techniques that violated every engineering specification. They only knew the tank ran, the gun fired, and the hedgerow cutter still cut through obstacles when needed. That was sufficient. In September 1944, 3 months before the tank would be first to enter Bastogne during the Battle of the Bulge, engineering perfection mattered less than operational availability. The hedgerow cutter's legacy extended beyond World War II. The specialized equipment designed for specific terrain became unnecessary in occupation duties and Pacific operations. Maintenance sections removed the cutters, returning Shermans to standard configuration. The tons of German steel that had been welded to tank bows were scrapped, melted down, and recycled into peacetime products. By 1946, fewer than a dozen hedgerow cutter-equipped Shermans remained in existence, preserved as museum pieces or training vehicles. Curtis Cullen lived until 1963, dying of heart failure at age 50. His obituary in the Cranford Chronicle mentioned his military service but did not refer to the hedgerow cutter. The few military historians who remembered his contribution were occupied with larger narratives: the D-Day invasion, the Battle of the Bulge, the Rhine crossing. A staff sergeant who solved a tactical problem using scrap metal didn't fit the grand historical arc. The story was too small, too technical, too focused on engineering rather than heroism. But the tankers remembered. The crews who breached hedgerows in July 1944, who survived bocage combat because their Shermans could move through terrain that should have been impassable, understood what Cullen's innovation had accomplished. They passed the story through veterans organizations, tank crew reunions, and informal histories. The narrative persisted not through official recognition, but through the memories of men who had trusted their lives to improvised steel prongs welded to tank bows by a mechanic from New Jersey who understood that perfection was the enemy of survival. The death ray inventors pursued weapons that physics rendered impossible. Hobart's DD tanks succeeded by working within physical constraints to solve specific tactical problems. Cullen's hedgerow cutter succeeded by ignoring engineering constraints to solve immediate operational needs. None of these innovations changed the fundamental nature of warfare. They simply made specific tactical situations survivable or winnable by men who would otherwise have died or failed. Modern military historians, analyzing the Normandy campaign with decades of hindsight, identify multiple factors that contributed to Allied success: air superiority, naval gunfire support, intelligence advantages, industrial capacity, and tactical innovation. The hedgerow cutter appears as a footnote, mentioned briefly in discussions of the Bocage campaign, credited to an anonymous sergeant, or attributed to collective innovation by tank crews. Cullen's name rarely appears in mainstream histories. The precise technical details of his design are lost, reconstructed from photographs and veteran interviews rather than engineering documentation. What survived was the principle. When confronted with tactical problems that formal engineering can't solve quickly enough, improvise using available resources and accept imperfect solutions. When bureaucratic approval processes threaten operational effectiveness, bypass channels and implement field modifications. When the choice is between doing things correctly or doing things immediately, choose immediately and refine later. These principles violated peacetime military culture, but proved essential to wartime effectiveness. The Sherman tank, maligned by critics for inferior armor and firepower compared to German designs, survived as a weapon system because it accepted modification and adapted to changing tactical requirements. The hedgerow cutter represented one of dozens of field modifications that extended Sherman's combat effectiveness beyond what designers had intended. Other modifications included sandbag armor, track shoes welded to hull sides, concrete-filled hulls for static defense, and improvised armored personnel carrier conversions. None of these appeared in the original engineering specifications. All proved tactically valuable. The German tanks that the Sherman faced in combat were engineering marvels. the Tiger with its 88mm gun and heavy armor, the Panther with its sloped glacis and high-velocity cannon, the King Tiger with protection that rendered it nearly invulnerable to Sherman fire. These vehicles represented the pinnacle of 1940s armored vehicle design. They were also complex, unreliable, difficult to maintain, and impossible to modify in field conditions. When they broke down, which happened frequently, they required specialized recovery vehicles, factory-trained mechanics, and parts that existed only in German manufacturing centers. The Sherman broke down less frequently, and when it did, a mechanic with a cutting torch and determination could keep it running using salvaged parts and improvised repairs. This distinction mattered more than firepower or armor thickness. Wars are won by armies that can sustain operations despite attrition, maintain equipment despite damage, and adapt tactics despite unexpected challenges. The Sherman, mediocre in technical specifications but excellent in reliability and adaptability, proved superior as a weapon system because it remained combat effective under conditions that rendered German tanks inoperable. 79 years after Kulin welded German steel to a Sherman bow, military forces worldwide still face the tension between engineering perfection and operational necessity. Modern armored vehicles incorporate sophisticated systems designed through years of testing and refinement, but when those vehicles deploy to combat zones, crews modify them using improvised armor, additional weapons, and field-expedient equipment that never appears in official specifications. The military culture that prizes proper procedure and engineering excellence coexists uneasily with the combat reality that demands immediate solutions regardless of regulatory compliance. The hedgerow cutter represents a moment when operational necessity overwhelmed bureaucratic process, when a staff sergeant with a cutting torch accomplished what engineering committees couldn't deliver, when improvised field modification proved more valuable than pristine design. The solution wasn't elegant, it didn't advance the state of engineering knowledge, it didn't win anyone medals or recognition, it simply allowed American tanks to drive through hedgerows in July 1944 when the alternative was remaining paralyzed in bocage terrain while German defenders killed American tankers at will. That was sufficient. In July 1944, facing terrain that threatened to stall the entire European offensive, Curtis Kulin built a device using scrap metal that restored mobility to American armored forces. The device was crude, improvised, and violated every principle of proper military engineering. It also worked, which was all that mattered. The mad mechanic who turned broken German steel into an engineering miracle wasn't mad. He was simply practical enough to recognize that perfect solutions requiring 6 weeks were inferior to imperfect solutions available immediately. The death ray never worked because physics forbade it. The swimming tank worked because physics allowed it with sufficient engineering. The hedgerow cutter worked because a mechanic ignored engineering entirely and welded steel to tanks using methods that would horrify proper technicians. War continued with weapons that actually worked, built by mechanics who understood that survival trumped perfection, that immediate trumped optimal, and that sometimes the best engineering was no engineering at all, just cutting torch, welding rod, and determination to solve the problem in front of you rather than waiting for someone else to solve it correctly.